Hi, I'm Jerry Luckenbaugh, and I'll be presenting our paper, teacher-student domain, or voice activity detection with teacher-student domain emulation, right? So, like many others, I'm working on VAD, the binary classification between speech and noise within a stream of audio. And this is an essential pre-processing step for many speech processing pipelines. And the main open problem that we're all working on is robust performance in realistic conditions, particularly for real-world applications. So I've split the history of the field into two categories, those of statistical methods, ones that rely primarily on the power of the extracted features within an audio stream to make assessments about these binary classification. So these often employ linear methods that are more interpretable, such as PCA, and but sometimes, as a drawback, lead to lower model capacities. And now we have the advent of deep learning since 2015, which allows us to learn more complex nonlinear relations between sequences of audio frames, and they tend to be more robust to non-idealities in data at the cost of actually having to gather large corpus of relevant in-domain data for training. So yeah, we want good VADs to have real-world applications. So in our case, we want to be able to use voice activity detection on smartphone data gathered from an onboard microphone in order to make assessments about a patient's mental states, particularly those with schizophrenia. And to do this, we use a transfer learning approach, which proves useful in adapting existing models that are well-trained on clean speech with good successes on those domains, adapting the successes of those models onto more difficult ones, like in the corpus that we gathered. So, right, this is all kind of started by an experiment we conducted a few years ago, and in it we gave a smartphone to two groups that randomly recorded bits and pieces of their week over 2 weeks. So these starting times are sampled pseudo-randomly throughout the day, but we were surveying them at regular intervals with various questions about their mental state and how they thought of their previous interactions within that window. So on the right figure, we have on the x-axis the number of reported interactions by participants within each group, as well as a combined group in blue. And we can see the average voice activity detected on the y-axis. And we can see in our combined group that the voice activity detected tends to increase with the user's reported number of conversations. And this indicates that we can quantify social interactions with these VAD solutions. So this experiment produced two relevant types of data to our study here. I produced these ambient recordings, which tend to be longer in length. They're of unprompted nature, so that's much better. But we have no control over the microphone placements or the number of speakers, and we have no control of whether or not people are speaking at all, so they tend to be sparsely voiced. And it also produced this survey data, which had an audio component where we prompted them with various questions about their mental health and how they feel. And these are typically shorter, prompted recordings with the microphone being fairly close to their mouth, with usually at least one speaker. So our methods rely primarily on this idea of teacher-student learning. It's a machine learning technique that relies on a few facts of well-trained models, particularly that they'll encode task information about the target domain through the sequential layer representations within a neural network. So These representations can then be leveraged to train new models on similar problems. And that's where we get this idea of a teacher training the student. It can support generalization of the student if the task domains are sufficiently similar. This technique can support supervised, unsupervised, semi-supervised approaches, and thus adapt the student to a slightly different, more difficult speech domain. So the bulk of our method is relying on this technique. So what we did was we trained our teacher with clean speech, corrupted that speech with noise, creating a parallel corpus with the equivalent information, equivalent speech information. And then when we trained the student, we penalized the student representations at the end of the network. We penalized it from straying away from the ideal representation of the unnoisy, uncorrupted data of the teacher. So this is done by a multitask loss function. This is just a convex combination of this mean square error task and a binary cross entropy for our binary VAD prediction. So this method relies a lot on the data that we use to corrupt our clean speech corpus. The clean speech, it's a fairly easy thing to gather. We have a proprietary data set where we did just that, where we prompted speakers with an American accent to speak into a microphone in a sound booth. And primarily, this is the easy part. The difficult part for us was to gather noise that was similar enough to our target domain. So the one solution we came up with was to just manually find this data ourselves in the target domain. We took a large chunk of the data set when we manually verified the lack of speech activity within each of them, yielding a little bit of data. But a much larger portion came from mining the QIIME5 corpus, which is a naturalistic ASR challenge for a dinner party scenario. And what we did was we took the time-aligned labels and we took the complement of the time-aligned labels, giving us the empty space between speech segments. And that produced much more. We also have babble noise, which we generated by just overlaying sentences from Timmit, and white noise, which is a standard evaluation criterion for speech activity. So the proposed method may be implemented with any kind of neural architecture. So one that we would like to emphasize are temporal models, which handle sequential data in a way that we can feed windows of context surrounding the frame of interest in order to get better predictions. So one that we use is bidirectional long short-term memory. But another one, which may be new, is the continuous state Hopfield network of 2020. It's a modern Hopfield network implementation with continuous states and an updated energy function, as well as giving us a new update rule. It was shown empirically and also theoretically by the creators that this update rule is equivalent to the self-attention found in a transformer. So we get more efficiency than using just the BLSTM network, but also similar performance to those of transformers. Right, so those are the architectures that we'd like to emphasize. We also used a fully connected layer just in a few experiments just to see how it compares. We've fixed the number of parameters in each of these networks just to control for any increases in performance due to this factor. We use ReLU activations for everything and layer norm regularization on the sequential layers. And not only can it be implemented with any model architecture, but also with any feature set. So the main ones that we explored in this paper were just the a 26 mail filter bank feature set, but also we explored the uses of 5 handcrafted features that came from the ComboSAD framework from Sajahi and Hansen. And as far as loss functions go, we use binary cross entropy for training the teacher on clean speech, and our proposed function for the student with a hyperparameter value of 0.2. Yeah, and we use the Atom Optimizer and trained on 4 epochs, just because the nature of this problem, with especially with layer norm, led to very fast convergence. Right, so getting into some of our results. Well, as we can see here in this graph, these are quantification of performance in terms of the F1 score for several data sets of interest. So if we look there on the leftmost of that graph, we have the ambient set, which we described previously. We consider this one to be the most difficult, as it's highly sparse and very uncontrolled. So, but we actually see a 7% increase in the F1 score from from our baseline, the robust VAD from Tan et al. So that's great. That's very encouraging for us. On the EMA dataset, we see that our methods are still competitive with our baseline, but it does seem like it's the LSTM is actually outperforming our Hopfield network on this one. And for clean laboratory speech, we also see improvements in our methods from the baseline, but this may primarily be due to a similarity between the training domain and the test set in particular here, because they were drawn from the same corpus. So we also wanted to see what happens under alternative simulated domains to gauge which conditions of corrupting noise most improve performance. So what we varied was the noise type that we used to corrupt our paired corpus for the student, and also the SNR of the data set used to corrupt it. So we see most often that generalization from the teacher to the student tends to increase when the noise condition matches the target domain. So not very surprising there, but this also indicates a similarity between babble noise, the chime 5, it was a dinner party scenario, and the target domain that we're interested in. And you can see this in the bottom right-hand corner. We can also see that the SNR of the system, the SNR of the corrupting noise, very much this method is very sensitive to that. And we can see that if we train on 0 dB, which is the test condition in all cases, we get the best performance despite higher noise signal to noise despite higher signal to noise ratios in the rows below each of the 0 dB conditions. We also conducted an ablation study where we examined the performance of a student when trained with a teacher and without one. And we can see that with our methods, with the teacher, we get performance increases. We get generalization increases on all of the test sets of interest here. So we also conducted another ablation where we examined the ComboSAD features that we mentioned previously. We combined these with the Mel filter bank features that we've been using in all of our experiments, and we found that the ComboSAD features tend to increase performance, although maybe a bit marginally, at the cost of a much higher computational complexity than just Mel filter banks. We also saw what happens under different context window sizes. We can generally see that more context leads to higher performance for both our Hopfield network and the BLSTM. But this this also comes at the cost of higher complexity. So yeah, in conclusion, this was a model agnostic, feature agnostic, domain adaptation technique for voice activity detection. You can find more details in our paper. Thank you for your attention.
Thank you to the speaker. Any questions from the audience?
Either online or in the room. We are monitoring the chat window if you are online.
Thank you. As far as I remember, Hopfield networks are from the 80s. It's associative memory network. Maybe you can say a little bit more about this network, because what the network should remember for the training, during the training, I don't see what will be the input to remember.
Right. So let's go back a little bit to that slide. Right. Yeah. So yeah, the continuous state Hopfield network, it's a novel architecture that's based on the Hopfield network of the 80s. But instead of just encoding the knowledge of the system via the fixed points of the linear system that you have in the traditional Hopfield network, this one has continuous states. So instead of only being defined for like linear transformations, they're applying like a nonlinear one. And this is in conjunction with their newly defined energy function, which is also different from the classical Hopfield networks. Yeah, so and they proved that this brings us a lot higher model capacities than those of the John Hopfield paper in the 80s.
Any other questions? I just wanted to ask about the data collection. So it seems like you were using some data from the sound booth, but also some that were recorded in the field when people were wearing the pins. I wanted to ask, what was the phone placement?
The phone placement in the field? So let's see. The field recordings, there was two types. So there was two types of data. The ones where we were asking them questions, and I guess we don't really have very direct control over their microphone placement. So it's but on average it's a few feet. So it's about an arm's length. But for the other field recordings, we have no control at all. So it's it could be all the way across the room, and we're trying to see if like any of this kind of noise would be helpful for training our networks with the existing clean speech.
So did you try to analyze the SNR distributions for these wild data?
This wild data varies. It varies rapidly. It varies much across samples. It varies across speakers. There's really not much that we can say definitively. The one thing that I noticed is that there were many regions of silence where there was not very much noise, maybe a fan running in the background, but there's other cases where they're in a party and this is everything else going on. So
thank you.
Could you say, did you develop an app, or did you ask the individuals to simply use kind of a memo or a record option on their phone?
Right, yeah, we developed an app. We didn't trust them to manually do that.
So that means that so is the app constrained? I don't want you to identify the manufacturer of the phone, but was it constrained to one type of phone?
Yes, it was.
Okay, that's good. So you have at least the consistency of the phones then.
Yeah.
That's good. Other questions? Could you try jumping to slide 13 just for a second?
13.
I thought maybe I had one question when I saw that.
Right.
So you were looking at the performance with and without, I think, the teacher-student learning piece. When you look at the differences without and with, for SAD, can I ask, did you see the types of errors that were corrected when you included the teacher-student SAD, or the teacher-student addition?
This wasn't something that we examined ourselves. These values were supposed to indicate like generalization of the student because they're measured with the area under the precision recall gain curve.
Okay,
So
all right. Okay. That's fair. All right. Any other questions? We keep looking on the chat here. We don't see any coming online. Maybe you're answering everyone's question already through the presentation. Well, let's thank the speaker again one more time. Thanks.